Hello everyone. In this video we are going to use our Excel sheet in order to help us do chi-squared goodness of fit, chi-squared test of homogeneity, and chi-squared test of independence. Okay, let's take a look at our scenario here. So it says a recent national report states that the marital status distribution of the male population 18 or older is as followed. Never married, 33%, married, 53%, widowed 2.4%, and divorced at 11.6%. The table below shows the results of a random sample of 1,780 men from California. Test the claim that the distribution from California is as expected at the alpha level of 0.1. Okay, so let's go ahead and let's grab our data. So we're going to grab our data, we're going to copy it, and we're going to come over to our sheet for it under the tab of chi-squared goodness. We're going to paste in our data in column B. And we see that they all pop up here. They just come up in alphabetical order. And then we have these yellow spaces for the expected counts. So in the expected counts, we need to place, we need to figure out how many do we expect to see. Now we get that by coming over here and looking at the percentages that were given to us. So we have never married as 33%. So we're going to say equals 0.33 times the total number of observations, which is summed up here as 1780. So that was for divorced. Oops, divorced was 11.6. So we got to make sure that we get this right. And let's get at 0.116 for divorced. Let's look at married next. Married was 53%. So that's going to be equal 0.53 times the total observations. Hit enter. Never married is 33%. There we go. So equals 0.33 times the total number of observations. And widowed is, where was it? 2.4%. So equals 0.024 times the total number of observations. And here we get our expected counts. So we have these expecteds, and that's what goes into our expected frequency. So if we look at our answers here, we've got, 587.4 for never married, and it's right here. So be sure that these are in different orders. All it is just alphabetical difference, and we get the right numbers. 587.4. Married was 943.4. 943.4. Great. Widowed 42.72. Great. And divorced is 206.48. So the correct statistical test to use for this is going to be a chi-squared test, and specifically the chi-squared goodness of fit test. So the null hypothesis is that the distribution is going to be the same for California as it is nationally. And the alternative is that it follows some other distribution. So our degrees of freedom are over here, and it's the number of groups minus 1. That's all that we have to do for our freedom. So it's not the number of observations minus 1 like we did in other times. It's the number of groups minus 1. So the test statistic that we get is going to be this chi-squared of 2.541. The p-value is given here as 0.46, 0.4679, and the p-value is going to be greater than alpha. So based on this, we should fail to reject the null hypothesis. So then our final conclusion here is going to be that there's insufficient evidence to conclude that the distribution of marital status in California is not the same as it is nationally. And if we look at this just like a layperson might look like if they didn't have any stats knowledge, they just kind of look at these numbers and like, yeah, they look pretty close. I mean, a little bit of differences, but not crazy, not enough to say that California isn't following the national average or the national trends. So let's go ahead and look at question 2. So now instead of just looking at one group and comparing it to a national average, now we're going to take two places and compare them to each other. So here we have a fisherman is interested in whether the distribution of fish caught in Green Valley Lake is the same as the distribution of fish caught in Echo Lake. So we're comparing these two lakes. So we have of the 367 randomly selected fish caught in Green Valley, we have so many were trout, were rainbow, other trout, bass, and catfish. And then we do the same thing for the other lake, for Echo Lake. And we're going to conduct this hypothesis testing at the alpha level of 0.01. Okay, oh, and on this previous one, I was supposed to change this from alpha of 0.05 to an alpha of 0.1, just so that we make sure that we do our comparisons correctly. Okay, back to our test of homogeneity. So let me go ahead and clear out these answers. All I'm going to do is just highlight them, delete them out, and let's zoom out just a little bit so we can see what's going on. So first things first, let's go ahead and grab our data. We have our location and our trout. I want to copy that. And I'm going to paste it in our orange cells. Paste special text. Okay. And look, so it has Echo Lake and Green Lake, and it has bass, catfish, other trout, and rainbow trout. So this is what we observed. Now there is some math that happens here, and it's in some of the other videos that show exactly how it does. And basically what it does is it takes the total in Echo Lake, multiplied by the total number of bass divided by the grand total, and that's how you get this cell right here for if there's no relation or if there's no differences in the proportions. Okay, so we have, this is what we observed, this is what we expected, and this is the chi-squared value for each of those. And we can then come over here to kind of see our observations, and we're going to test at the alpha level of 0.01. Okay, so first thing, what should we do? So because we're comparing two groups to each other, and we're looking at the distribution of fish in each of them, this is going to be a chi-squared test of homogeneity. And so the null hypothesis is that the distribution of fish is going to be the same in Green Valley Lake and Echo Lake. And the alternative is that it's not the same distribution. So our test statistic here is going to be our chi-squared again, this 15.6847, or rounded to 3 is 0.85. The p-value, 0.0013. And the p-value is going to be less than our alpha, and we are going to reject the null. So then our final conclusion is that there is sufficient evidence to conclude that the distribution is not the same. And let's go ahead and take a little bit of a deeper dive into this. And we can see it's like, where were the big differences? So the big differences were in the rainbow trout. So notice in Echo Lake, we saw 210. And if there was the same distribution between the two, we would have expected to see 237. So that was like a kind of a drop there. In Green Valley, we saw almost 200, but we expected to see only 170. So Green Valley like overperformed and Echo Lake underperformed. And so we can see that it's like these distributions, they're different than what we had really expected. And anyways, you can go look at some of these other ones, but the chi-squared kind of tells you like where the big differences are. So we had big numbers here, and we have relatively big numbers in the bass too. Look, Echo Lake outperformed, like we saw 91, and it was expected to only see like 78. And Green Valley underperformed. They actually saw 44, and they were expected to see 56. Okay, so that's how you do a chi-squared test of homogeneity. Now let's do a chi-squared test of independence. Now the interesting thing is chi-squared test of independence and homogeneity are identical mathematically. The only difference between them is that how the data is collected. So in the fish one, we were looking at these two lakes and we were looking at the distribution between the two. Now this next one, we're going to say a researcher is interested in investigating whether a living situation and pet ownership are dependent. So what they're going to do is they're going to go out and measure somebody and ask them two questions, instead of going somewhere and like asking just one question and comparing it between the two locations. So it allows you to do a different interpretation of the data, but the math is the same between homogeneity and test of independence. So let's go ahead and grab our data. So family status and animals, we want to copy it. And let's go ahead and paste it in. Paste special, text, click OK. And here we see that we have cat, dog, none, and various, and couple, family, and single. We see these are what we observed, this is what we expected, and we can see here if we see any big differences. And if we notice, like right off the bat, like none of these look like huge chi-squared differences, so let's go ahead and look. So first of all, the correct statistical test would be a chi-squared test of independence, because we are looking at these like kind of two variables on a person, and we are trying to compare them between a whole bunch of different individuals. Okay, so the null hypothesis is that there's no relationship between these two of ownership and living situation, and we can call that, if there's no relationship, that they are independent. Whereas the alternative hypothesis is that they are dependent. So the test statistic, let's scroll over. For our, let's change our alpha level too, because I think our alpha level is 0.05. So let's take care of that right now. Okay, so our chi-squared is 0.34. Let's make sure, 0.3047. And the p-value that we get is 0.8029. So this is a huge p-value, and which basically means that like, hey, they're pretty much independent. It doesn't look like that your family status is really changing your pet status. And so our p-value is greater than alpha. Based on this, we would fail to reject the null. And Thus, the final conclusion is that there is insufficient evidence to conclude that pet ownership and the living situation are dependent. So that's how you go through and you do kind of your enhanced categorical chi-squared tests on both goodness of fit, test of homogeneity, and test of independence. Best of luck to you on your own problems.